Good morning once again. In this lesson we'll learn about logs. Alright, now I'm sure you must have heard of logs before. Logs is actually a different way of writing a number. Mainly in science and maths, you would write a number in its log form. It has certain advantages when you write a number in its log form. Alright, now I'll just give you a quick example of when you would use a log form. So let's say you were talking about the exponential decay of atoms, unstable atoms undergoing radioactive decay. Alright, so let's say you started off at the beginning, you started off with 1 million atoms, and after 1 year you have 100,000 atoms. Alright, and after 2 years you have 10,000 atoms, and after 3 years you have 1,000 atoms. So 4 years you have 100 atoms, and 5 years you have 10, 6 years you have 1, and 7 years you have 0.1 atom. Alright, so if you were to sketch this on a graph, it's going to be a bit difficult. If you were to say time against number of atoms, it's going to be a bit difficult because the it's the number of atoms against time. Time is on the x-axis, number of atoms is on the y-axis, because you're going to have a very large y-axis going up to 1 million, and it needs to come down to 0.1. So your y-axis is going to be extremely large. So rather than sketching a number of atoms against time graph, if I do the log of n, so if I call this n0, n0 is equal to the log of n, it'll look something like this. 1 million is going to be 6, 100,000 is going to be 5, 10,000 is going to be 4, 1,000 is going to be 3, 100 is going to be 2, 10 is going to be 1, and 1 is going to be 0, 0.1 is going to be minus 1. Alright, so if you were to sketch a graph for log of n against t, it's slightly easier to sketch because you got values going from 6 through to minus 1. Alright, we'll learn in a moment how these transform into these. Alright, so but this is where you'd use logs. Alright, in a situation like this where you have numbers which have a very big range, and makes it very difficult to sketch on one axis those numbers because of its big range. So you find the equivalent log forms of those numbers and then you sketch them. Alright, okay. Now before I start off with the logs, you need to be familiar with the exponential graphs. Alright, so you are used to functions such as these: y is equal to 2x, or y is equal to x plus 5. Y is equal to 2x may look something like this. Y is equal to x plus 5 may look something like this, with the intercept at 0, 5. The exponential graph, which is y is equal to 2 to the power of x. Alright, if I were to sketch this graph, how would that look? So let me just take some values for x, and these are values for y. So if I say x is, let me start from the big value here, x is equal to 3, that makes 2 to the power of x, which is 2 to the power of 3, which is 8. X is 2, 2 to the power of 2, 4. X is 1, 2 to the power of 1, which is 2. And x is 0, 2 to the power of 0, so 2 to the power of 0. Okay, this is an important thing you're going to learn. I'm sure you know this also previously from Core 1. Anything to the power of 0 is always 1. Alright, and x is minus 1, that is 2 to the power of minus 1, which is a half, which is 1 over 2 to the power of 1, which is half. So if I were to sketch this graph will probably look like this. Let me draw the axis first. 6, and that's 8. So at 3 it's at 8, at 2 it's at 4, at 1 it's at 2, and at 0 it's at 1, and at -1 it's at half. So let me use another color to draw the graph. So the graph is going to look something like this. And as it goes further into the negative scale, now if you make x equal to -2 rather, it's going to be 2 to the power of -2, which is 1 over 2 to the power of 2, which is 1 over 4. 1 over 4 is a quarter. So, and also if I say when x is equal to -3, which is 1 over 2 to the power of 3, which is 1 over 8, which is 0.125. So as you go higher in the negative scale, the value of y becomes smaller and smaller. It never approaches 0 though. It becomes very small, but it never approaches 0. So it runs almost parallel to the x-axis. So therefore you have an asymptote on the x-axis. But because the asymptote is on the x-axis itself, we can't show that dotted line. So we don't draw the asymptote. Alright. So the same thing could be done for a different graph, a different function. So let me change the color. I think it's still in black. Yep. So 2, not 2 this time. We've already done 2. So y is equal to 3 to the power of x. So this time, also if I do -1, 0, 1, 2, and 3 for my x coordinate, my y coordinates would be 1 over 3, 1 and 3, 9 and 27. So if I were to compare that to my graph of 2 to the power of x, it probably would look something like this. So 3 would be somewhere here, 2 would be somewhere there, where x is equal to 2, y is equal to 9, and 3 is 27. It's gone way beyond the graph, so it's probably somewhere there. And at 1 it's the third, so it'll be below half, below the half point here. Alright, so if I were to sketch that graph, but if you notice at 0 it's 1, so that's the only point it's common to both the y is equal to 2 to the power of x and y is equal to 3 to the power of x. That point there, when x is equal to 0, y is equal to 1, that is common to both graphs. So if I were to sketch this graph, try my best, this probably, oops, go below, below. There we go. It'll look something like that. Alright, and if you were to draw the y is equal to 3 and 4 to the power of x, you would expect it to be above these two graphs, whereas on the other side it will be below these two graphs. Okay, so that's how you draw your exponential graphs. Okay, now we'll come back to logs. Alright, so I showed you an example where you might use logs to make your data representation simpler. Alright, now this is what logs is all about. Alright, so if I say 2 to the power of 3 is 8, and now I'll have to write this in log form, I'd say log of 8 to base 2 is equal to 3. Simple as that. Alright, so the 2 becomes the base. Alright, the base of that log, and 3 is basically the power to which 2 has been raised to get this number, this result. So log of 8 to base 2 is 3. Alright, let's look at another example. So this is log of 9 to base 3 is equal to 2. Alright, so 3 is the base of this log, and 2 is the power to which 3 has been raised for you to get this 9. So let's look at an awkward indices. So let's say it's 2 to the power of -1. Alright, that you all know is a half. So again, I'm going to write this in log form. So that's log of half to base 2 is equal to a -1. Alright, So the power to which 2 has been raised is minus 1. Okay, now let's look at this. 16, square root of 16 is in fact 16 to the power of half. 16 to the power of half is in fact 4. So log of 4 to base 16 is equal to half. Alright, so the power is always the result of a log. So log of 4 to base 16 is half. Okay. Okay, now we'll go back to this table and see how we've got these results here. Alright. If you look at your calculator, you have a log key, and on that log key, if you press 100 and if you press log, no, you press log first and then you press 100, you'll get a result of 2. That basically is this. If I say 10 to the power of 2, it's equal to 100. Okay, so in maths, if you don't specify the base, it's taken to be 10. Alright, so log of 100 to base 10 is 2. That's why you had a result of 2 in this table. And if I look at the next or the previous number, so 10 to the power of 3 is 1000. So log of 1000 to base 10 is equal to 3. So in maths, usually if you don't specify the base of the log, it's taken to be 10. That's why in that example, when I took logs of these numbers, it was to the base of 10. So log base of 10 of these numbers were these. So these are the powers to which 10 had been raised to get these numbers. Okay. Let's look at a couple of more examples. Okay. You got log of 2 to base 8, which is equal to a third. So if you were to write this in standard indices form, how would you do that? So you would notice that this value here, the base, is always the number to which you raise a power to, and that power is always the third, or the number that is the result of the log. So that's the power. So 8 to the power of a third is equal to 2. Now that's a bit peculiar, but some of you would realize that a third is actually the cube root of a number. So the cube root of 8 is in fact 2. So that does work out indeed. Let's look at this example. It's a minus half. Let's look at this example here. Alright, again, 4 to the power of a negative half is equal to 0.5. How does that work out? Alright, when it's negative, it's the reciprocal of that number. Alright, so it's 4 to the power of half, it's underneath the 1 is equal to 0.5, and 4 to the power of half is in fact the square root of 4, which is 2, so half is 0.5. Alright, so let's look at some other examples. Okay, let's look at these. Okay, you have these to solve. Alright, log 12 to base 12. Okay, and you'll have to work out what that is. So the answer to any log question is always a power. So this will make this unknown power, we'll call that x. So x is the power to which this 12 has been raised, and the answer to that is 12. So I've written this in indices form, what was in log form. So many of you would know that to get 12 to the power of something, if the result of that was 12, that something would be, that unknown would be just 1. So x is 1. So log of 12 to base 12 is in fact 1. Let's look at this.